Okay, so today is the first of like another back-to-back set of lessons that really I would, if it wasn't for time considerations, I might consider putting them, right together as one big lesson. But there's no way that it's reasonable to put this one and topic 6 together. So today we're going to talk mostly just about the theory behind magnetism, and then tomorrow we'll talk about the mathematical equations behind it. Does that make sense where we're going here? So today, if you've looked through the notes, I don't have any work for us to do, which will be kind of nice because it will give you guys a chance today just to work on whatever else you're working on, your assignments or your labs. So tomorrow we'll show you the last two equations that are in the magnetism section and the electrostatic section on your formula sheet. So, okay, let's begin. I'm going to do something a little more today that I rarely do because I hate it. You guys know this, but I'm going to read it more off my notes than I typically do just because this is really like today is story day. We get to teach you about like the history and the legends and the theory behind magnetisms. So from what I was able to research, the reason why it's actually called magnetism is based on this guy named Magnus, a shepherd from 800 BC who was the first guy to discover a magnet, I guess. He discovered a rock stuck to his shoe. Or sorry, a nail stuck to his shoe. Yeah, rock stuck to the nails in his shoe. There we go. All of it put together finally. So, I mean, you guys have intuitive knowledge of magnets by now, right? Like, you've seen them before. Like, my 2-year-old daughter gets how magnets work to some degree, right? She doesn't know that there's north and south poles, but, I mean, she understands that the magnets stick to the fridge, right? So, again, like we've been talking about in this section here, I mean, this is why this is under the forces and fields section. There's definitely a, there's got to be a field in play, right? Because if there is a force of attraction between Cameron's fridge magnet and the fridge itself, then there must be a field causing that action at a distance. You guys recall me using that phrase, right? Action at a distance, a way to describe that, this and this are going to connect. That action at a distance was due to gravity. We've already seen some electrostatics. Now we're adding magnets into it, right? So, what he was able to discover, or at least maybe not Magnus specifically, but other, I don't know, people who were playing around with this at the time, they discovered that if you put a sliver of magnetic rock on a little bit of water, it would point north. And essentially, that's what a compass does. Like, if you guys have seen a compass, not like the one in your cell phone, right, but like a real old-fashioned one that we'll play with, right? You just have like a little liquid surface. You put a little piece of metal on it, and it would spin until it actually faces north. Okay? So we now know that they have poles, north and south. So, we're going to get to this later in the notes. Which way does the north part of the magnet point? South. And therefore, the south part of the magnet points north, which is actually weird because our compasses, they point to what we call north, but that's actually magnetically south. You guys ever heard this before? Read this part in the notes? The North Pole, spoiler alert, this doesn't shatter your illusions here. The North Pole is not the North Pole. It's actually the South Pole. Because that's why the compass points towards it, right? The north end of a magnet, right? I mean, don't we know this from electrostatics? Positives attract negatives, negatives attract positives, positives repel positives. If the north side of a compass is getting attracted towards what we call north, then it's not really north at all. It's actually south. So I got some photos of that later in the notes if you've seen that far, but like mind-shattering concept here. The North Pole is actually the South Pole, guys. So if you want to disillusion your like nephews and nieces or like Kinsey Ann, tell her that Santa lives at the South Pole. Really mess them up. Anyways, let's keep going through the notes. So, okay, you guys know what I mean when you refer to it as a pole of a magnet, right? Like the two different opposite sides. So many different magnets will have different shapes to them. Here's a very typical one. This is a bar magnet, and you guys are going to get to play around with this next week, Tuesday, in the lab as well, where you basically have your two different sides, your north and your south side pole here, and it's similar to electric charges, right? You have your positives and your negatives, but there's one huge difference here. I can separate the negatives from the positives when it comes to charges. However, magnets always have to have a north and a south pole in the magnet. And I'm going to show you this on another slide here just because I'm thinking of it now. If you were to, come on, where's the pictures? Sorry, don't bother flipping here. Why do I not have the pictures of it? Sure, I have a picture. Okay, apparently I don't have a picture. If you were to break a magnet in half, you cannot break the north half away from the south half and just have a north and just have a south. If you break a magnet in half, it recreates new norths and new souths. Does that make sense? So you actually can't have what's called a monopole. Shh, I had monopoles in my notes somewhere.
You have a note about it on the page. Yeah, on that.
This one right here? Ah, here it is. Okay, I don't have a picture though. Where did I see the picture? Maybe it was in the readings I'm giving you tomorrow. Okay, anyways, this is the note here is what I'm trying to refer to. If you try to break a magnet in half, it just creates smaller magnets. So you can't actually have, if you want to write it in, it's called a monopole. Theoretical physicists are actually currently working on trying to discover monopoles. They think if they can find basically just a purely north magnet or just a purely south magnet, they figure that it can help them with their string theory and their overall, what's it called again? They want to do their unified theory of physics kind of things. So there's even a Big Bang Theory episode on it. Did you guys watch Big Bang Theory? When was it again? It was years ago. It was an episode where Sheldon, Leonard, the whole gang of them, they went up to like the North Sea. It was right before Sheldon, Penny, and Leonard got back together again for like the second or third time, and they ended up going to the north, like almost to the North Pole, at the end of one season. They were going to look for what they called magnetic monopoles. It was actually the title of the episode. I was thinking about that last night as I was prepping for this. It was called the Monopole Expedition. Anyways. That's what physicists are looking for. If they'd like to try to find a way to make a magnet that's only one pole, but to the best of our knowledge, at least as of when I Googled this last night, they haven't found a monopole yet. But they're looking. So, okay, let's talk about this side here. Magnetic fields are similar to the electric fields, but the big difference is magnetic poles always come in their pairs. So, let me just read through this, like the three types of fields you need to know about them, because these are the three. We're not holding out on you. This is it. So. You've got your magnetic fields. They're fairly strong, which you guys probably intuitively know because, I mean, we were able to see and kind of feel the electrostatic forces when we played around in the lab the other day, right? And I know that gravity exists because watch, right? But hopefully you'd agree, if you've ever played around with your fridge magnet, magnets are pretty strong, right? Like I can feel the force of attraction between them, right? Or repulsion. In terms of our magnetic fields, we don't do a ton of calculating with them. Okay? I'm going to get a little ahead of myself, but tomorrow when we do the math on this, a magnetic field is represented by the letter B. So if you guys see the letter B in some of those formulas, we'll get to that in a little while. But we don't actually have a whole ton of formulas involving it. We just calculate it in relation to the forces involved. So most of our formulas will compare B to like a force. Magnetic, maybe? Is it M the subscript they use in those formulas you've got there?
Yeah.
M, magnets. So, yeah. So we're going to talk about the math behind that tomorrow. Magnetic fields are going to be able to do attraction or repulsion. How would you have repulsion? Well, you just have the north end of a magnet push on the other side of the north end of a magnet, and then you can feel them repel. They're related to the magnet involved, whereas like these guys are the masses and the charges, and this is the biggest difference of all of them, like I've been saying here. We have not been able to find a magnetic monopole yet, but they predict that one day we'll be able to. Maybe not in my lifetime. So, while I'm talking about this slide here, I should give you a little piece of advice. I was reading up about the diploma exam, and they suggested a possible question on a diploma. That was the worst Venn diagram circle ever. They were suggesting a good idea for a question would be to compare a gravitational field to an electric field to a magnetic field, and like they could do a Venn diagram where you talk about some of the similarities and some of the differences between them. Okay. And so the example question they had right here would be if this was A right here, what would be an example of a statement that you could write in that location? Yeah, good. They both attract and repel, right? That'd be a good example there, right? Whereas if you were to ask for a statement that could go for this one here, you might say these ones right here, they only come in pairs, right? There is no ability to have just one or the other. So, anyways, while I'm thinking about it, three-way diagram of Venn diagrams, they suggest that would be a good prep for diploma exams. Okay, I skipped a little bit of stuff on this slide right here. There are only 4 metals that I've at least researched. Maybe there's more. But these are the main 4 metals that are known to be able to have magnetic fields attached to them. So you got your iron, your cobalt, your nickel, and your gadolinium. So gadolinium, I'm a chemistry major, and it's like, we never use gadolinium. So the main 3 are probably the top 3. And maybe you've heard this bolded word before. Sometimes we call them the ferromagnetic. You guys heard that, like, ferro is like a Latin prefix for iron. You guys heard that before? Okay. That's the starting here. If you ever hear fer, that's probably Latin, I believe. Latin for iron, which probably means that they chose that word because most original magnets were made out of iron at first, and then we then realized that, okay, you can make a magnet out of nickel or cobalt, but we still call them ferromagnetic. Okay, what else should I talk about here? There are different shapes that we can have for magnets. I found this diagram online to illustrate 3 main ones, and I will let you guys play around with magnets later next week. The 3 big ones are a bar magnet, just like a button magnet, and the horseshoe magnet. And each of them have a different way of having a north-south pole. For example, this could be the north and the south pole of that magnet there. This could be, say, the north-south pole of that magnet there. Any ideas how this magnet would differentiate? Yeah, good, like top and bottom, yeah. So top and then like bottom. Top and bottom. Could be the magnetic poles there as well. So we're going to have to talk about magnetic fields as well. Right? Because if we recognize that there must be a magnetic force of attraction, right, we can see that action at a distance, then there must be a field as well attached to it. So we're going to need you guys to be able to draw field lines similar to electric charges. Here's where it talks about monopoles. Okay, I knew I had it in here somewhere. So you guys can read this. Eventually, we predict monopoles, but no one's been able to. Here's the theory why. They believe, the theory is what they call domain theory. They figure that each individual electron spinning around the nucleus has the ability to create its own mini magnetic field. Basically, it has to do with electrons and spin and stuff like that. And if all of those individual little pieces, if you can kind of imagine them on like a chunk of metal here, if they all line up nicely and they align, then they figure that that's the reason why a magnet's being created. So, I don't need you guys to know the ins and outs of that, because really, this is just trying to figure this stuff out, really. Right? Like, we know what a magnet does, but to explain why it does it, it's not like you can hop on Miss Frizzle's magic school bus and shrink down to the size of an electron to see what's happening, right? So we have some theories. But anyways, that's the idea, is that if all of these domains all align, then that must be a properly applied magnetic field. If they're kind of just going here, there, and everywhere, then it probably means that it's not magnetized. So here's kind of another idea of it. You can almost imagine that this chunk of metal, this big magnet here, right? If all of the atoms kind of line up, and they're not all haphazard, but all of the atoms, all of the electrons are lining up in a proper, direction, orientation, then now you have a north side and a south side of a magnet. And if you were to ever cut this magnet in half, imagine you were to slice it right here, well, now this would become a new south, that would become a new north. Does that make sense? Hence the reason why we're struggling to find a monopole. Okay, if those domains can get locked into place, it creates permanent magnets. And you guys, those are the ones that are on your fridge, right? Those are the ones that you play around with where, they'll stick something to your locker. But it's actually possible for you to make a temporary magnet as well. And sometimes these are very useful in technological advances where, let's say you want the magnetic field to be able to be switched on or off, and you temporarily want a magnet, or later you don't want a magnet. Sometimes we call those things like electromagnets. You ever heard of that before? Where you can create a magnet using electricity. We'll get to the theory behind that tomorrow. For example, I once did one of those puzzle rooms. Do you guys ever do those where you have to escape the rooms? You heard about these before? And one of the cool things about this particular room is that they had a huge electromagnet keeping one of the walls in place. And as soon as you solved one of the puzzles and you managed to turn off the electromagnet, well, then the magnet wasn't there anymore. You could literally move the secret wall out of the way, right? That would be a good example of a temporary magnet where it's only functioning when you want it to. Right? Other things that might involve like a magnet like that would be alarm systems. Right? If you can kind of envision the idea of you have a window in your house and you don't want it to be opened up, right? As soon as, say, the magnet has gotten pulled away, perhaps that will then change an electric field, and then that electric field will end up setting some sort of alarm. So you can actually use like magnets and electricity kind of interchangeably. You know what I'm saying now? Okay, anyways, I'm getting off these notes again here. You can demagnetize them though. The main two ways are you either drop it or like you really mess it up by throwing it up against the wall. If you misalign those domains, then you can demagnetize something. The other one is you heat it up, right? And then the rationale behind that is, well, what is heat? Well, heat just increases your motion. If you increase the motion, especially of the electrons, then again, they may not be aligned. And so there's something called the Curie temperature, which from what I understand is a magnet ceases to work if you heat it up to a certain point, so each one has its own temperature for that. So if you heat it up to 5,000 Kelvin, well, now it's really no longer functioning as a magnet. So, okay. I already pointed out that we use the symbol B in formulas. I don't actually know why they chose B, only because every other letter had been used at least once, if not twice. So B is a good one. I can't think of what else I'd use B for, actually. Brightness. Anyways, the unit we use is capital T for Teslas. Okay. And this has actually changed my understanding in the last, let's see, I graduated high school in 2001. Sounds old. When I was in high school, we didn't use Teslas yet. When I was in high school, I learned this unit right here called a Weber, a WB. And since then, physicists, I think, have come to the conclusion that it's a little bit ridiculous to have all of these possible units be available for magnetic field strength. Because actually all of these were considered something they could use. So I learned this. I learned Webers over meters squared. That's the unit I was taught. Hopefully you'd agree, though, that, like, isn't this ridiculous to have all of these as be possible units you could have for a magnetic field? That's insane, right? So in the last little while, there seems to be a general consensus to let's just go with just this one here, capital T for Tesla, and that makes it a little bit simpler. So I do want you guys to know that a Tesla is made up of other unit types, right? Like you've got your primary units of meters, kilograms, seconds, moles, those sorts of things. Whereas these units right here, these are all like derived units. So they all involve things like meters and seconds and coulombs, right, like your base units. But we've just simplified it to capital T for Tesla. You guys can kind of read the middle stuff I have right there. Here's a frame of reference. Earth has a magnetic field. We know this because of the fact that we can see how a compass will align with self. It doesn't align with north, it actually aligns with south because South Pole is actually the North Pole. Anyways. So Earth actually has a magnetic field, but it's actually not all that strong. Because really, let's say you were holding a magnet. Right? Would you get sucked to the North Pole? Would you be like, whoa? It's not going to pull you all the way to the North Pole, right? So there is a magnetic field around the Earth, but it's relatively weak in comparison to, say, a fridge magnet, a lab magnet, or a star itself, may end up having a magnetic field that's, well, considerably larger in terms of scope. So, magnetic fields are strong. Electric fields are somewhat strong, but gravity is much weaker in comparison. Right? Now, hopefully that makes intuitive sense, right? I cannot feel the gravitational attraction between me and my keys, right? I can feel it between me and the Earth because the Earth is so big, but there's no feeling gravitational attraction, right? We know it exists, right? You guys were probably able to feel a little bit in the lab the other day there, where you could like, you use like the pith ball and the rod, you could like push the ball a little bit further away, right? You can probably feel that to some degree. But I guarantee you, when you flip the magnets, you'll feel whoa, there's a little pull there. Right? So. Okay, let's get to the theory then of what you're going to be tested on and what you need to be able to accomplish and do. So my first thing I want you to be able to accomplish is know how to draw a magnetic field line. Okay. You just have to know the rules similar to electric field lines. So you know how electric field lines are what a proton would do, a hypothetical proton? Well, a magnetic field line is like what a hypothetical compass would do. And since a compass is basically a small magnet, it's the direction the north end of the magnet would point. Long story short, a field line points towards the South Pole. Because a magnet, like a compass is basically a magnet, right? Able to rotate, basically. It's a rotatable magnet. That compass would point towards south, which we call north. Poorly chosen. Anyways, so yeah, all you have to do is just point the arrows towards the south side of the pole. These guys right here, they definitely curve though. Okay, what ends up happening is like it's gonna have to point away from north. But like, let's say you were sitting over here, it's not gonna want to keep pointing that way because it's gonna kind of want to some degree, be able to say, well, hang on, there's a south pole way over here, right? But it has to kind of go the long way around. You can kind of envision that. So if there's a magnetic field and it's curved, we would actually consider it to be the tangent line. That's my point number 3. You remember what a tangent is, right? What's a tangent? Yeah. So like at this point right here, the magnet on the compass would point like that way. Whereas if you were right here, the magnet on the compass would point that way. So it's at like any given instant moment. We'll play around with these on next week, Tuesday. So yeah, basically draw your field lines as though it's what a compass would do. A better way of describing that is always away from north towards south. Just memorize that. Magnetic field between two magnets. Yeah, magnetic field between these two magnets would be similar then to how we calculate voltage. You know how voltage was known as like your potential difference, right? I mean, in a way, yeah, we don't exactly have like an electron or a proton that's going to get sucked from one side to the other, but isn't it kind of going to be similar here, where the field between the north and the south, wouldn't that be fairly uniform between them? Right? And if you had, I don't know, I mean, hypothetically, if you could have a monopole, right? Let's say you could just have a north. Well, the north would get sucked from one to the other, just like a proton or an electron, right? It doesn't exist yet because we haven't been able to find them, but maybe they exist somewhere. I just realized I skipped over something I should talk about back here, these bolded words. When we talk about field strength, you know how there were other words you should know when it came to voltage, like potential difference, electric potential difference. You should be aware that if they talk about either magnetic flux density or magnetic induction, we're talking about the same thing. So those are other words for field strength. Oh, and the way we measure it, just so you guys are aware, in physics here, we don't worry about too much about how we measure it except in relation to force. So the formulas involved are going to involve a force, but the way you would calculate it otherwise is how much torque there is on a compass needle. Okay. You guys know what like torque is? Oh, it's like, I don't know, it's like a circular sort of like, yeah, I don't know. Yeah, that's a good definition. Yeah. As you go like around a circle, like imagine like putting the lug nuts on the tires of your car. Right? You need to have a lot of torque and like a circular motion to do that. So if you had a compass needle that was supposed to go north say that way, and the compass needle was this way, the amount of torque that it takes to like force it that way, that's how we calculate magnetic field strength. So the stronger the field, the more it's gonna pull it that way. Imagine that you like added a little bit of resistance to it, right? Well, if the magnet was strong enough, it would be able to overcome the resistance and still point north. Does that make sense? So that's essentially how we calculate our magnetic field, is how much torque it requires to move the compass needle. Okay, here's some pictures of magnetic fields. Let's draw in some arrows, because they don't actually have arrows drawn in. So magnetic fields are drawn away from north and towards south. So if I were to draw some arrows here, they'd be going like this way and that way and this way. And like these ones are kind of going outwards, away from the north and into the south. Does that work? I mean, some of these pictures are going to look very similar to the pictures you would have drawn between protons and electrons and stuff like that, because if you have two north arrows, then really they're both trying to point outwards. And you kind of almost have like a gap in the middle here, right? Where there really is no field. At least there's nowhere near as much field. For these ones right here, this one's kind of cool. The way this will work on this one here is that it'll point in between here. You'll have a nice uniform field, right, between the two sides of the bar magnets. But then as it comes further out, it will actually have a little bit of curvature as it goes like that. And it'll do the same thing right here. Right? You'll have to curve around the edges. Oh. Yeah, totally. All right, you guys can draw the last one. Okay, so last main thought, and I've got a ton of pictures for us to look at. The Earth is essentially a giant magnet. Back to Magnes of 800 BC, they start realizing that it sure seems like if I put a piece of metal that's magnetized on a little strip of water, that it always points the same direction, always points north. Unfortunately, that was another one of these conventions where whoever decided to make north be north didn't really know the theory behind what was happening until afterwards, and now it's hard to change it, right? Because really, north is magnetically south. Does that concept make sense to you guys? Right? But because the north side of a needle points that direction, they decided to say, well, the north needle points that way, that must also be north. But really, the Earth's magnetic field is actually opposite, right? So the other thing I need you guys to know is the magnetic pole and the geographic pole are actually different. Okay? There's actually two north poles and two south poles, and they're all in the wrong spot. So you have to completely rewrite what you know about this. Okay? Magnetic north is where, if you treat the Earth basically as a big magnet, that's where magnetic north is. Okay? But where we think that Santa Claus lives, the geographic north pole, that's actually a different location because that is where the Earth spins. You guys know how the Earth spins around, right? But the Earth is not straight up and down. It actually has a little bit of tilt to it. So if you imagine that you had a basketball and you put two fingers on both sides like this, and then I have there you spin it around like that, the geographic north poles are where the Earth actually spins from. But those aren't actually where magnetically the poles are. So there's actually two different locations. And they're a little bit different. There's about a 1,500 kilometer difference between the two, actually. So when you're using a compass way down here on the 49th parallel, you really don't notice a difference because true north might be there and magnetic north might be there, and you can't really see the difference. But if you were up in the Arctic, you really wouldn't be able to use a compass anymore. Because if you're looking for the geographic North Pole, it might be here, but true north, magnetic North Pole might be way over there. Right? The closer you get to the actual poles itself, the more off it's going to be. And then the other note I have here we've been talking about, the north magnetic pole is actually in the south, and the south is in the north. So let me show you a whole bunch of pictures here. That's really where we're going to end. So here's where the north magnetic pole is about. But geographically, that's where Santa lives, the geographic North Pole. I don't actually know where Santa lives. It really matters to kids, but if I try to explain this to my 4-year-old, I mean, as well tell her it's not Santa. But there's actually two North Poles. Actually, but neither are North Pole, they're both South Poles. So, anyways, actually, you probably could still call this the geographic North Pole. That might be fair to say, but this is actually not the North Magnetic Pole. Technically, this is the South. In terms of how that works. So, here's another picture I found. Apparently, physicists believe that the magnetic pole is actually moving. And there's actually some theories that the Earth has reversed polarity a couple of times in its history, where north used to be south and south used to be north, and for whatever reason, it's actually flipped. And so the South Pole actually used to be a South Pole, and the North Pole used to be a North Pole, and for whatever reason, it's actually changed around. So, but apparently, this picture right here kind of illustrates how the actual magnetic North Pole has been slowly but surely migrating in some of these islands way up here in northern Canada. Here's a picture I found for the South Poles, which really are North Poles. Again. Okay. So here, right off the coast of Antarctica, depending on, I don't know, what time of year it is and how much ice mass there is out here, this is where magnetically south would lead you to, or north would lead you to. And then here is the axis upon which it actually rotates. So this would be a fixed location, because the Earth is always rotating on this axis. But this one right here seems to also be migrating as well. Here's a picture then kind of illustrating how Earth does then have a magnetic field. We would then draw it, as to how how an actual compass would work. And so these field lines are now drawn properly if we draw them like this. Because the way a field line is supposed to work is it's supposed to go away from north and towards south. And now that I've blown your minds and told you that south is actually north, does that make sense though? Right. Because this is actually the south pole magnetically, we just call it north. Right. So we would draw field lines then like this coming from the southern hemisphere towards the northern hemisphere. Hence, when you're standing right in that vicinity there and you have a compass in your hand, the compass in your hand will point towards north, which is really south. Anybody ever heard that before? Like, anybody ever knew about this whole north-south conundrum? It does make logical sense though, doesn't it? Right? If a compass has a north needle, the north needle on a compass does not actually point north. It should point towards the opposite pole, right? So anyways, magnetic north, and hopefully you guys can see how this right here, these guys here, would be the axes upon which the Earth actually starts doing its rotating too. So. Another picture kind of illustrating the same concept. I think this one's a little better here, right? Up here, they've actually shown you that this is south and this is north. So I feel like I said the same thing over and over again. Another picture sort of illustrating the same sort of thing. This one's probably the best one of all because it's actually drawing everything correctly in terms of field lines, right? The field lines are going out and around like this, which means that they are pointing towards the south, but it's geographically north, it's magnetically south. So, three main highlights, none of which you really need to do a whole lot with. Okay. First main highlight, I need you guys to know the similarities and differences between electric fields, magnetic fields, and gravitational fields. So, biggest differences and similarities on this one, they can attract and repel, depending on how you orientate your magnetic fields, but you really can't cut them in half like you can with gravity and with electric fields, right? I can separate me from my keys, right? There is a field between me and my keys, and I can move them, right? I can physically separate the two masses. I cannot physically separate the north and south poles on the same magnet, right? If I have this magnet and this magnet, sure, I can separate those ones, right? But on an individual magnet, monopoles have not been discovered yet. Second main thing you should know is the units and the direction that we assign to the field. So field is a capital B. The units are Teslas, which really a Tesla is made up of so many other unit types, kilograms and coulombs and stuff like that, right? And we define a field as to what a compass needle would do, which is it would point towards south and away from north. And then third thing, I need you guys to know that really we lied to you all these years about the North and South Pole. It's way more confusing than that. There's really like 4 poles, 2 norths and 2 souths, and south is really north, and north is really south, and neither of them are really in the same place because one's based on rotation and one's based on the magnetic field. So, yay. That's about it. Fair enough? Okay, so I'll stop there because it's been half an hour plus. So tomorrow we're going to talk about electromagnets and the left-hand rules. But here's what I'd like you guys to do in the meantime today. If you guys can, read through some of those pages, just in terms of just some other background information on the basics of magnetics. And then tomorrow we'll cover some of the math behind it. Sound good? So read through that, and otherwise just work on your labs and your assignments and all that sort of stuff. So, I guess while you're packing up here, one last thought. Here's our schedule for the next little while then. Today and tomorrow we're going to do a couple lessons. Thursday, Friday, we've got some work time. Next week, Monday, will be our last lesson. So we're actually done as of 2 more lessons. I've got topic 6 and 7, and then we're done. Next week, Tuesday, we're going to do another lab, which will be really similar to the last lab. There's no conclusion, there's really no purpose other than I'm going to have some stations, and I want you guys to play around with magnets. Right, so similar kind of concept. You won't get shocked nearly as much as you did last time around. And then that's next week, Tuesday. I can't remember which day I put it on, but either Wednesday or Thursday we're going to run our second quiz. And then the following week, Monday I believe it is our unit test, something along those lines. Maybe I should pull it up on the screen here. Yeah. Say that again?
Do electrons still have gravitational force?
Oh, absolutely, yeah. And it's very small, right? There's actually some theories about the 4 main types of forces. There's the electromagnetic force, the gravitational force, the strong nuclear force, and the weak nuclear force. And the question is about the strong nuclear force as to why do electrons not get gravitationally pulled into the nucleus? And why do electrons not get electrostatically pulled into the nucleus, right? Because in theory, both of those things should occur, right? You know what I'm saying? Electrons are negatively charged, the nucleus is positively charged. Why does the electron not go into the nucleus, right? You'd think it would, right? Same thing with gravity, right? Electrons have a mass, 9.11 times 10 to the minus 31, right? You would think that they should, kind of like you or me, be sucked into the nucleus, kind of like you or me is attracted to the surface of the planet. But they're not, right? So although they do have gravitational fields, that's where the 4th force comes in, the strong nuclear force, where we're really not sure, at least I don't know how that works, but they're trying to figure out, well, why do they behave the way they do? It probably has to do with the wave-particle duality of electrons, where they can act as a wave or as a matter. They can actually behave like light and do things like diffract and refract and stuff like that. So, yeah, that's cool stuff.
Alright, so we're getting this now.
Okay, give me 1 second. I just want to show you the schedule just to confirm I have it right. And then yeah. Alright. So here, now you guys can maybe visualize it a bit better. So lesson today, tomorrow, work days till the end of the week. Last lesson next week, Monday. Lab Tuesday. Quiz Thursday. Oh, okay, so apparently I didn't put your unit test on Monday. I put it on Tuesday. Okay. One more thing I should tell you guys about. The following week, Monday, after that Monday the 20th, we are going to write what's called a field test. And I don't know how you guys are going to pull it off, but I'll figure out how that works. Basically, it is a practice half diploma. Okay, we'll count for marks, but what you're able to do as teachers, and I've got one set up for us hopefully, is it's only on units A and B, so the field unit we're just finishing and on momentum, and basically you get to write a practice diploma, but only on half the curriculum. Okay. And it'll just give you a chance just to assess how well you're doing so far. So
Should we head there for that?
I don't know how we'll pull that off. It's digital, so we might be able to just give you the codes and you can just do it online. Because you actually have to use a computer to input your answers. You know what I'm saying?
Yeah, we have lab tests here, yeah.
Yeah, so we could probably just give you the entrance code VC-wise. My only worry is I'm supposed to supervise it, so I don't really know how that works.
We can just like set the camera up underneath this.
I'm sure we'll figure out a way. So I don't see any point in you guys coming here if it's digital though.
Gotcha.
Anyways, just so you guys know, it's not for marks. Like I don't put it in your mark, but it'll give you guys it'll give you a halfway checkup as to how well things are doing halfway through the year, right? So if it goes well, yay. If not, don't worry about it. I wouldn't like study for it like crazy though, right? Just write it and see how it goes. So, anyways, that's kind of our next month. Somewhere in there, I'll be gone though, right? At some point, I'll be gone for a couple of days because we're having another kid. So depending on what it is, we'll do some rearranging. But I'm hoping that if we have our baby, like we're due on the 23rd, so if we end up having our baby somewhere around in this time here, it's not the end of the world. I mean, you'll miss out on some questions, but you can still email me or something like that still too, right? Okay, sound good? Okay, we'll talk to you guys later then.
Is the field test only on momentum and field strength?
Yeah, so it's basically it's half. And then we'll write another half one at the end of the year too.
And the diploma's only going to be on this year.
Yeah, only on 30. Yeah, not on 20. That being said, like you still need to know like Newton's second law. You still need to know your kinematics formulas. But yeah, they're not going to specifically test you on kinematics.
Gotcha. Sounds good.
Okay, we'll talk to you guys later.
Alright, see you, Shulk.
Okay, take a break or whatever you guys need. Go for a walk. We'll you guys have half an hour left to work on stuff then, I guess.